moment maps. And we have understood that these functions on the manifolds appear both in the transformation rules of the fermions and, even more importantly, in the potential. It is clear that we are concerned with studying the spaces that emerge by putting moment maps either equal to 0 or equal to some constant. This constant, by the way, are the Fayet-Iliopoulos terms I mentioned before. This obvious question that arises in gauge theories actually leads to a technique to construct new, non-trivial Kaehler, HyperKaehler geometries from trivial ones that is called the Kaehler quotient or the HyperKaehler quotient. It was realized historically. Some of you told me yesterday that you are appreciating my historical remarks, so I will make you happy with some other more recent historical remark. The birth of the idea of Kaehler, HyperKaehler quotient can be historically located quite precisely, both from the chronological point of view and from the geographical point of view, in the late 70s in one place, Stony Brook in the United States, on Long Island. At that time, in Stony Brook, that ITP of Stony Brook, that was for many, many years the Institute of Theoretical Physics, was headed by Nobel Prize laureate C.N. Young, and that is also the place where Peter van Nieuwenhuizen was appointed just at the end of the 70s, one of the three inventors of supergravity. There is a very important mathematical institute as well that is just one floor below the ITP, the Institute of Theoretical Physics, so there is a very active group. And other historical figures in the early development of supersymmetric theories, like Martin Rocek and some visitors, among them Lindström and Carl Hede from Sweden, happened to be there, and other people, including myself and other in this organization of the school, have been visiting Stony Brook many times, or there for some periods. So at that time in Stony Brook was written a paper that is the beginning of all this story. The paper was written by Martin Rocek, Carl Hede, Hitchin from Great Britain, who is quite well-known historical mathematician, the heir of Sir Michael Atiyah in Oxford. But he visited Stony Brook and he was passing by. Lindström and Carl Hede, they were all there at some time, and they wrote this paper that is precisely called Kaehler Geometry and Supersymmetry. That was the paper where the idea of making a Kaehler quotient was clearly expressed in a mathematical way, showing that it has a physical realization in gauge theories. From that point, the idea made a long trip through mathematics, became the preferred technique for mathematicians throughout the world to construct new Kaehler geometry, starting from all the flat ones, was used by people that try to construct example of restricted holonomy manifolds. It was generalized to HyperKaehler. From Kaehler to HyperKaehler is quite obvious trip. And at a certain point, it was used by another distinguished mathematician from Britain, Peter Kronheimer, who is presently professor of mathematics in Harvard, that made an extremely important paper at the end, instead of the 80s, 10 years later, using the technique of Kaehler, actually HyperKaehler quotient, to construct so-called Hale manifolds, asymptotically locally Euclidean manifolds. Asymptotically locally Euclidean manifolds are the gravitational instantons, are the manifold, the four manifolds with Euclidean signature, so after Wick rotation, like that have a self-dual Riemann tensor. So are the analog for gravity of the instantons. Instead of the field strength, it is the Riemann two form that is self-dual. These manifolds are called asymptotically locally Euclidean because, as all instantons that are sort of lumps with decaying at infinity, this matrix are tend at infinity, in some sense defined, to the flat metric, so to flat space. But if you are very careful, you see that it's only locally, because the manifold at infinity, at r equal infinity, is not the three-sphere, as it is for normal R4. R4 is just at infinity. I mean, it's the bundle of three spheres if you use polar coordinates. But it is the three-sphere divided by, look, by what? Divided by a discrete subgroup of rotations, one of the Kleinian groups we have discussed in the first and the second lecture. So they are locally Euclidean, and the whole thing is just this, that you cannot have an instanton that is really flat, absolutely flat. It is only locally flat. The discrete subgroup defines the metric. And it was Kronheimer who showed that by means of a construction I want to tell you how the discrete group defines a Kaehler manifold, and then by means of a Kaehler quotient we obtain precisely the asymptotically locally Euclidean instantons. And he showed that this is the only thing that is a complete classification of Hale manifolds. One class that corresponds to the cyclic group was known previously. It was constructed independently from the Kaehler construction by other two quite well and distinguished scientists from Britain, namely Gibbons and Hawking. The Gibbons-Hawking metric, that are multi-center metric, are precisely the gravitational instantons corresponding in Kronheimer construction to the case of cyclic groups. But then there are all the other groups, the dihedral and the three exceptional ones, that are quite, I mean, at the end, the explicit solution of the algebraic equations that give you the final metric may be difficult to be solved explicitly, but Cronheimer showed that this is a complete classification and that the problem is reduced to this set of equations. And the homology cycles of this non-trivial manifolds as an intersection matrix that is, namely, you call intersection matrix the matrix where you say that a cycle touches another one, so there is a link between. You make points for each cycle, and if one cycle intersects the other, you put a line. So you construct some diagram. This diagram is the Dynkin diagram of the corresponding Lie algebra that, because of the ADE correspondence, corresponds to the group you have, the SO3 group you have constructed. So Cronheimer construction is the third incarnation of the ADE classification and corresponds to the resolution of the singularities C2 over gamma considered by Arnault. So the cycle is closed. And ADE, as I told you, is the main theme of my lectures because it unites supersymmetry, group theory, algebraic geometry, and all the structures invented by, in geometry invented by supersymmetry. So my plan is now to discuss Kaehler quotient and to show you in detail the precise construction of the easiest, simplest of this Cronheimer manifolds, Ale manifold, that was independently constructed in '79 by two scientists at the time working in Stanford, the Japanese Toru Iguchi and the American Anson. Chris, I think, is Anson. The Iguchi-Anson metric. The Iguchi-Anson metric is the simplest possible in the list of self-dual metrics, gravitational instantons, corresponding to the simplest possible group, Z2, the group with two elements. And you see that it's already not too easy metric. The others are more complicated even, but one should suffice to see the whole picture. Okay? So this is my plan. And I would like to stress that since the gravitational instanton, the Kaehler quotient construction, etc., can be seen from many different viewpoints, I would like to mention that the Kaehler quotient, in that case, is HyperKaehler. But there is the Kaehler that is suitable also not only for C2 over gamma, but for C3 over gamma as well, is at the heart of the ADS4 CFT3 correspondence, in particular this very famous ABGM construction. So, what are HyperKaehler quotients? We have learned what is the moment map, and once we looked at those equations, we decided that if the Lie algebra of the group we are considering as a center, a non-trivial center, then we have the possibility of these Fayet-Iliopoulos terms that mathematically are just numbers valued in the dual. It's an n-tuple of numbers. Sorry, it's an n-tuple times 3 numbers in R3 cross the times the dual of the central of the Lie algebra. In other words, for every generators of the center of the Lie algebra, we can introduce three real numbers, okay, that are Z. Yes, of course. No, but they break it spontaneously. Well, Fayet-Iliopoulos terms are supersymmetric objects, in the sense that you can add to a Lagrangian that is supersymmetric these terms without breaking the supersymmetry of the Lagrangian. Then, of course, all the vacua that you obtain from a supersymmetric theory with non-trivial Fayet-Iliopoulos terms usually are breaking supersymmetry. But it's a spontaneous breaking of supersymmetry as usual. It's like X model, right? You don't break gauge theory. You simply obtain a spontaneous breaking of gauge theory. Fayet-Iliopoulos terms are precisely conceived to break supersymmetry in a supersymmetric way, right? In a spontaneous way. And from this point of view, I mean, from the point of view of mathematicians, what it is, we simply write the equation that you have the moment map of your quaternion HyperKaehler. In this case, I'm focusing on HyperKaehler. You have this HyperKaehler manifold, and you have some group that acts on it in a triholomorphic way. And we learned how to construct the corresponding moment maps. For each index I that enumerates the generators of the Lie algebra, we have a triplet of moment maps, okay? And then we say that this is not equal to 0, but we say is equal to some z of x of I, whenever I belongs to the center of the Lie algebra. For all those moment maps that are not in the center, we write the equation okay. Those that are not in the center, we put equal to 0. Those that are in the center, we put equal to some numbers that we invent. Okay? Then we say that we have defined a surface, and the usual terminology is to call this a level surface. It's a level surface in the manifold, and we define originally a manifold S. We have some manifold that I call S, that is the manifold admitting the action of this group. And in this manifold N, S, I define a surface called N, which is explicitly given there. It is the locus, the algebraic locus, from I, union on all I, of the counter image of Z. In other words, it is the locus satisfying the equations I mentioned above. Now, this locus, just because of the equivariance of the moment map, is obviously invariant under the action of the group G. Since the moment map is equivariant, and since the only levels that have been given a value different from 0 are those in the center of the Lie algebra, if I make a transformation of the group, the locus remains invariant. If I had given a value to levels that are not in the center, of course, a transformation of the group will change the locus. But if it is in the center, by definition of the center, it will remain invariant. So once I have defined such a locus n, I can take the quotient of that locus n with respect to the group itself. So I take the space of orbits of the group inside the level locus. And the final outcome is that if I have a group of dimension G acting on the space of dimension S, then the result of these two operations will be a manifold of dimension dim of S minus 4 dimension of G. Minus 4, it is obvious, because I impose 3 conditions for each element of the group. For each generator of the group, either this or this is a condition. So it is 3 times the dimension of G, and a fourth is obtained by the final quotient. So the dimension of M is dimension of S minus 4 times dimension of G. Okay? So the important thing is that in this way, one can obtain a manifold, and this is the general theorem, which is very important, is that if the original manifold was HyperKaehler, the manifold I obtain by means of this construction is also HyperKaehler. And there is an explicit way of obtaining the corresponding Kaehler potential. The corresponding Kaehler potential is obtained by means of this very interesting formula. Given a vector field that is a Killing vector field, I can complexify its action by introducing an I. The action of the original group on the locus, we know, is 0, in the sense it leaves it invariant. But the complexified, if I introduce an I, whatever it was, no longer leaves the locus invariant. So what happens is actually that I can always find a complexified version of a transformation that acts on the level 0 surface and brings it to the level I am interested in. I can obtain the solution of the equation P moment map P of S equal Z by taking the solution P of S equals 0 and multiplying by S by a special E times V. This is a sort of condensed notation. I mean the action. I mean the action of the complexified group on the manifold, such a way that the solution of the equation from that was solution of the equation at level 0 is mapped into the solution of the equation at level z. So this is the only equation that at the end has to be solved to find v such that this is true. And at the end of the day, we will see that this is an algebraic equation. If you are able to solve this algebraic equation, you have the solution for the new Kaehler potential, because the new Kaehler potential is the restriction of the original Kaehler potential to the locus plus this vector v defined by this multiplied by z. And we will see an example in the Higuchi-Hanson case how solving this equation you will precisely obtain the Higuchi-Hanson metric. So let's now discuss the beginning of what is the core of my lectures, the Hale manifolds. The Hale manifolds are, as I told you in my, so to say, philosophical or ideological introduction, gravitational instantons. And I already mentioned that they are spaces, Riemannian spaces, whose metric tends to be the flat metric at infinity, but the boundary at infinity is not the three-sphere, it is the three-sphere divided by a group gamma, where gamma is a subgroup of SU2, of SO3 or SU2. Actually, now, the point that I will try to advocate in my last lecture tomorrow is that this manifold can be seen altogether as the HyperKaehler quotient defined in my previous transparencies of a flat manifold that is simply C2, it is simply C to power 2 times the order of the group gamma. Gamma is what defines the manifold at infinity, and gamma, we already know the classification, because it's a finite subgroup of SU2. Given this gamma, we know the order of the group, and we can take C to the power 2 order of gamma. Then there is an appropriate, always, an appropriate group that has dimension order of gamma minus 1, and taking the HyperKaehler quotient of C2 with respect to this group, we precisely obtain the resolution of the singularity C2 over gamma, and this resolution is precisely the Hale manifold. So this is the program for tomorrow, and I think it's convenient to stop here.